Okay, 11.6 is a really important section. Brings a lot of things together. It turns out there's different types of convergence. You can have what's called absolute convergence, you can have conditional convergence, and you can have divergence. So you have to understand the definitions really well. So the definition of absolutely convergent: a series is absolutely convergent if the absolute value of the terms, the series of absolute values, is convergent. So right off the bat, what that says is if you have a positive term series that converges, if every term is positive and the series converges, then it's absolutely convergent because the absolute value of each term is just the term. So that's one thing. But it's possible to have some cases where the absolute value of the term series might not converge, but yet the whole series might converge, say by the alternating series test, for example. Anyway, we'll see some examples of that. But this is the definition of absolutely convergent. Now, if I ask you a question, determine whether the following series is absolutely convergent. This first one, we can look at the absolute value of the nth term. If you take the absolute value of the nth term, we are determining whether this series converges absolutely. Look what you get. When you take the absolute value of the nth term, the negative alternating part goes away and you have this. And this term is less than this term, obviously, because the denominator is bigger. And furthermore, this series is a convergent P series. Don't say this converges. That doesn't make any sense. This series converges. So by the comparison test, I know that this series converges. If this series converges, then that means that this series is absolutely convergent. So this series is absolutely convergent, you see? So take the absolute value of the terms, and if that's the series with the absolute values converges, then we say the original series is absolutely convergent. Okay, this is a biggie right here. This is a real important one right here. Look at this series right here. We've seen this before. This is what we call the alternating harmonic series, right? Well, notice, if you take the absolute value of this term, you get 1 over n, and we know that the series of 1 over n is divergent, so this is a really good example. This is not absolutely convergent. This series is not absolutely convergent because if you look at the series of absolute values, you get the divergent harmonic series. You may recall in our last video, we showed that you could use the alternating series test on this. Remember, we did that. So this is an example of a series that's not absolutely convergent, but it still converges from the alternating series test. We'll come back to that in just a second. We have a name for that. In fact, we have a name for that, what I just said. If a series converges but not absolutely, so if the absolute value terms, that series diverges like we showed here, but yet the series still converges. Remember, we showed this converges by the alternating series test. This has a name. This series has a name. This is an example of what's called a conditionally convergent series, okay? If the absolute value terms, the series doesn't converge, but yet the series still converges, perhaps by the alternating series test. Another theorem says if the absolute values if the series of absolute values converges, then the series itself, it also converges. That's a nice theorem to use. So now what we're going to do, this is something that you should pay close attention to. I'm going to give you a series. I'm going to ask you, is it absolutely convergent, is it conditionally convergent, or is it divergent? What I would do is first determine if it's absolutely convergent. That's my advice. And if it's not absolutely convergent, but it's an alternating series, then I would apply the alternating series test to see if it might be still conditionally convergent. Okay? So first determine if it's absolutely convergent. The absolute value terms is n over ln of n, right? Now, does that an even go to 0? I'm not so sure that an goes to 0. What is the limit as n goes to infinity of this? Well, you use L'Hopital's rule. This becomes 1. This becomes 1 over n. So the limit, you get the limit as n goes to infinity of n, which is infinity. So it turns out this series is not absolutely convergent because it fails the test is that the nth term doesn't go to 0. It turns out, however, bad news for the alternating series test as well. If the nth term doesn't go to 0, this, you can think of this as b sub n, or they call this a sub n, but we actually call this b sub n. The nth term of this does not go to 0. Isn't that one of the conditions for the alternating series test? So we showed it's not absolutely convergent, and then since the nth term does not go to, it should be, let's call this b sub n. B sub n would be this without the alternating part. Since this does not equal 0, it fails the alternating series test too, so that's why it diverges. Got it? Let's do a couple more. This one here, so the question is, does it converge absolutely, conditionally, or diverges? We always first test to see if it converges absolutely. So look at the absolute value of a sub n, we get this. And the absolute value of sine n over absolute value of n squared, but you don't need the absolute value bars here. You do know, however, that isn't the absolute value of sine n less than or equal to 1? So it looks like I'm going to compare it to this series, right? This series is a... By the way, I want to mention, this is not a positive term series. This is a really good example. This is not a positive term series. Some terms are positive, some are not, some are negative. But it's not an alternating series either, is it? So this is a good example of a series that's neither alternating nor positive term. But anyway, the absolute values of them is a positive term series. And so I've shown that the absolute value converges by the comparison test. So if the absolute value of the terms converges, then the whole series is absolutely convergent. Got it? A couple more things here. There's a couple of tests we're going to look at in this one. My favorite test is called the ratio test. It's going to be used a lot, especially towards the end of the chapter. It works really well with factorials and things to powers. But it says, if you look at the limit as n goes to infinity of the ratio of the nth plus 1th term over the nth term, the absolute value, whatever that limit is, if it exists and it's less than 1, then the series is absolutely convergent. If the limit's greater than 1, then the series diverges. And if the limit of the ratio equals 1, then the test is inconclusive. What does that mean? That means you'll have to use a different test, perhaps the comparison test or the integral test or something. Anyway, here we go. So let's look at this. I mentioned it works really well with factorials. I think we've seen this before, maybe not. But if you look at the ratio of the nth plus 1th term to the nth term, a sub n plus 1 is right here, you see? It's n plus 1 factorial over n plus 1 to the n plus 1. And a sub n would be this. This is a sub n down here. Okay, so look, it's kind of a lot of work here, but you could multiply by the reciprocal, right? You get this. Then, like I did before, you can break off an n plus 1 and call it n plus 1 times n factorial. And you see this n plus 1 to the n plus 1. Let me break off one of those factors of n plus 1. So then you get n plus 1 times n plus 1 to the n. Okay? So the n factorials, can you see why the n factorials cancel? And the n plus 1s cancel, and it simplifies to this. You might want to hit the pause button and think about that for a minute. Then I'm going to write it like this, and this looks like it has an indeterminate form. You're getting 0, this is going to 0, this is going to infinity. So remember how to look at the limit there? If you let y equal this expression here, and then the natural log of y is this, we can take the limit as n goes to infinity of the natural log of y, and whatever that equals, our answer is going to be e to that, okay? So we've done this before. When you take the natural log and move down the n, it has an indeterminate form, when you take the limit at least, of infinity times 0. So what you would do is you could rewrite it, move this n down to the denominator and call it 1 over n on the bottom. Now it's kind of messy, but you could apply L'Hopital's rule to this. The derivative of the top is the reciprocal n plus 1 over n times the derivative of what's inside by the quotient rule. And then you end up with, on the bottom, you get the derivative negative 1 over n squared. It's kind of a mess, actually. But when all the dust settles, this just becomes 1, doesn't it? And then you can cancel one of the n plus 1s. So you end up with this. You might want to look at that, which is just this. And this actually has limit negative 1. Be careful. That's really important that it's negative 1. You know why? Because the limit of the actual ratio, remember this is the log of, we took the limit of the log of the ratio. So if the limit of the log of the ratio is getting close to negative 1, the ratio is getting close to e to the negative 1, which is less than 1. So therefore, the series is absolutely convergent. It's quite a lot of work, isn't it? All right, let's do a couple more. This one, we could use the ratio test on. I'm going to show you a better test, but if you tried the ratio test here, you see what's going on. You get a sub n plus 1 is this, and I'm going to multiply by the reciprocal of a sub n. So you see what I did? This is a sub n plus 1. This is the reciprocal of a sub n. That's a nice way to write it. Save some time. Now what you can do here is, do you see why you can break off a 2 and then you have 2 to the n, but that will cancel with this one? And then what you end up, you have a 2 left on top. And then if you break off a n plus 1 as a factor, you still have n more factors of n plus 1. So you could write it like this. It's kind of a pain. Anyway, we get down to here, and then what I'm going to do is, I know that this limit's 0. I'm going to see what this factor is getting close to as n goes to infinity. So I'm going to do what we just did. I'm going to let y equal this factor. I'll let you fill in the details, but when I let y equal this, and when I take the log of y and I look at what happens as n goes to infinity of log of y and apply L'Hopital's rule, I get 1 over e again. So look, getting back to what I was trying to do, if the first factor is getting close to 0 and the second factor is getting close to 1 over e, the whole thing is getting close to 0. Now remember, if the limit is less than 1, so this is 0. So it was a lot of work. I'll show you a better way to do it in just a second. But we use the ratio test to show this is absolutely convergent. Whenever you have a, this is the last thing I want to talk about. Whenever you have a series where you have things to powers, you see how we have numbers and values of n raised to a power. The root test looks almost exactly like the ratio test. It's same kind of conclusion, but when you take the limit as n goes to infinity of the nth root of the absolute value of a sub n, instead of taking the ratio. Okay, if the nth root of absolute value of a sub n goes to L less than 1, this series is absolutely convergent. If it goes to a number greater than 1 or goes to infinity, this series is divergent. And if it equals 1, the test is inconclusive. So look at how much easier it is to do that one we just did. All you have to do is look at I'm doing the exact same problem we just did. Only now if you look at the nth root of this, well, the nth root is going to cancel with these powers. I have the absolute value, so the negative goes away. So you just have this, because the nth root cancels with the nth power. This is 0 less than 1, the series is absolutely convergent. So that's a great example of one where sometimes the root test might be more helpful. Okay, we got 2 more here. Let's look at this one here. So I'm looking at this. I'm wondering. Let's try the root test. Why would I try the root test? Because see how you have something to the 2n power? You could think of that as being to the n power that's squared. So look, when you have this thing to the 2n power, the n's cancel, right? And so you have the limit as n goes to infinity of this to the 2 power. And you can apply L'Hopital's rule, and I believe you get 3 squared. I guess you could also just take the limit inside the square and think of it that way too. It's 9. If it's bigger than 1, that means it's divergent. All right, one last one here. This one's kind of hard. It's hard to understand what this even says. This here is saying that you're multiplying. This is all one term here. You take all the odd multiples up to 2n plus 1. The one that comes before this one, by the way, would be 2n minus 1. So you're just taking all the odd multiples up to 2n plus 1 over n factorial. So this is what I'm saying. What is a sub n plus 1? This is really kind of tricky here. Watch. A sub n plus 1, you replace n with n plus 1. You see that? That's really important. You see how I took n and I replaced it with 2n plus 1? And so on the bottom, when you replace n with n plus 1, you get n plus 1 factorial. So this becomes 2n plus 3 on the top. Now, what does that mean? The factor, I should say, that's right before this one would be 2n plus 1. If you think of it that way. Anyway, so that's what I just said here. So this is a sub n plus 1, okay? A sub n plus 1 is this. So when you use the ratio test, I wouldn't use the root test here because I don't have anything to a power. Anyway, if you use the ratio test, this is a sub n plus 1. This is the reciprocal of a sub n, and you can kind of see what happens. These all cancel with these, and you have a 2n plus 1 left. This n factorial cancels with this one. Anyway, you end up with this. The limit as n goes to infinity. Turns out to be 2, which is greater than 1. After all that work, the series diverges. We'll see you next time. Bye-bye.